So this is some guidance on how to figure out what you're doing for Part C. Now Part C is actually going to use some of the data that we found in Part A. So the stuff you're looking at here, there's 0.80, 0.20, 0.0010, 200 seconds on the average reaction time, 5.0 times 10 to the negative 6 molar per second. That's what we found for Part A in that reaction. And if you recall, that was actually done at a certain temperature, and that's going to be important too, 22.0 or 20.0. What I'm going to do there is, since they're different, I'm going to find the average of those temperatures. So, and this will become the temperature that will end up down here. It will be put into Kelvin, but the temperature is going to be 21.0 degrees Celsius. We're going to convert that into Kelvin. That's 273.15 K. Once we take significant figures into account, it's going to be 294.2 K on the temperature. So that's what's going to go in here, 294.2 kelvins. The average reaction time, that's going to be what we got from up here. That's the 210 and the 190. That's how it came out to 200 on that one. That was for that reaction 1 there in Part A. The rate was 5.0. I'm going to put some units here, molar per second. That's 5.0 times 10 to the negative 6. Again, we got that from Part A. The K value, we get that by taking the rate, which we have here. So that's the rate. And the concentrations are the same concentrations as we have here, 0.80, 0.20, 0.0010. That goes in here. 2V specific powers that we also found in Part A as well. And that'll give us the K value, which came out here to be 780. When we take the natural log of that, that would be, to get this, I'll just put this in the calculator, be K equals 780, and ln of K, just by putting that in the calculator, comes out to be, I think it's 6.66. And that's correct for significant figures as well. You always have the same number of decimal places in the log as you have significant figures in initial number. So that's 2 versus 2 here, so 6.66. And we've got 1 over temperature here, and 1 over temperature would be 1 over T is equal to 1 over 294.2 K, and that comes out to be 3.399 times 10 to the negative 3. And the unit there is K to the negative 1 because it's 1 over K on the temperature. So you're going to do the same thing here for the others. We have these temperatures that we're going to use. We've got 13.5 and 14.5. I would just find the average of those, and that's what would go down in here. And the 42 and the 41, and the average of those would go down in here. So just go down to do that. So the average of those. Now the average of these as well, the 42 and the 41, that goes in the 40 degree section there. The average reaction time, again, we've got the times here. Those are going to go in here and here. And then we can calculate the rates. The rates are always going to be based on the concentration of I2, which in this case is going to be the same for everything, divided by whatever time we get here and here. So the same as what we did in Part A, basically. The K, we're going to calculate that based on the rate, which we already have, divided by all of these different concentrations to those different powers. That's how we're going to come up with those K values. And then we can get the natural log of K and the 1 over T as well. Now after we've done all that, we're going to end up with 3 values of natural log of K, 3 values of 1 over T, which we can end up graphing. Now the graph is likely for you to end up looking something like this. So you'll have temperature will be on the 1 over temperature will be on the x-axis, and that has the units of 1 over kelvins, or kelvins to the negative 1. And then you'll have your ln of K, which will likely be negative values, to be honest, down here. You'll end up with a graph that will end up looking something like this. As you can see, it has a negative slope on it, if you look at the direction here. Now there's two things you can do here to find the slope, and we're going to need to find the slope of this graph. And the reason is because we're given this equation here, and as you can see, we've got ln of k on the y-axis, we've got 1 over t on the x-axis, and the m, or the slope, is going to be this negative ea over r. So there's two possible ways we can get this slope. If we put it into Excel, we can get the slope directly off Excel. Or if we're going to use a hand graph here, then what we would do is we would do this graph, and those 3 points are the points we're given. And these points here that I'm actually doing here are actually on the line of best fit. And the slope then is going to be the delta y, I should say, delta y over delta x for those specific points, the ones on the line of best fit. And that's going to come up with a value. And that value is going to be used here. We have the m, which we're going to get from down here, off the slope of the line of best fit. So that's going to go in here. And the r value is actually a constant value. And I believe that it's 8.314 joules per mole per Kelvin. And the slope here will have the unit of kelvins, because it's going to be change in y over change in x. So it'll be 1 over 1 over k for the unit, which will be k for the slope. So that'll have a unit of k. So you can see that if you take the slope and you multiply it by r, then you'll end up with a unit of joules per mole, which could end up being converted into kilojoules per mole by multiplying by 1 kilojoule over 1,000 joules. And that will end up giving you kilojoules per mole as the unit for EA. And that's what we're going to end up doing.